Hi everyone, my name is Armen Donigian, and today I'll be showing you what a recommender system is and how you can build one using TensorFlow to make your digital experiences more personalized. But first, let's figure out what problem recommender systems solve and why you should care. Recommender systems are a solution to a growing need for personalization. For example, Amazon helps us find what we're looking to buy. Netflix helps us find interesting content to watch, while Google helps us find things we're searching for. These are all examples showing a growing need to personalize content by leveraging machine learning. For today's lesson, we'll focus on the problem we're trying to solve: how to build a personalized movie recommender. Our solution will be to use movie features to recommend new movies based on what users have liked in the past. Now, let's take a look at our data. Our data consists of 4 users, Ren, Danielle, VJ, and Chris. 6 movies, Star Wars, Dark Knight, Shrek, Incredibles, Blue, and Memento. We also have a user movie rating matrix. Each row corresponds to a user, and each column represents a movie in our database. The value in row I and column J indicates the rating from 1 to 10 that user I gave movie J. For instance, Ren has rated Star Wars with a rating of 4. Before we go further, let's take a look at the 5 steps we'll need to build our recommender. The first step will be to initialize the dataset. We're then going to scale the movie feature matrix by ratings of each user. Then, we'll find the user feature matrix, followed by computing the inferred movie rankings, and finally, we'll close off by determining the movie recommendations for each user. Now here's our user movie rating matrix from earlier, next to our movie feature matrix. The movie feature matrix is a K-hot encoding of the features we are using to describe our movies. For example, Star Wars belongs to the action, sci-fi, and drama genres. Each row corresponds to a single movie, and a 1 indicates that the movie fits that genre. Note that we leave an empty value for any genre which the movie doesn't belong to. Let's initialize the dataset by creating lists for our users, movies, and genres using TensorFlow. We can initialize these as constants in TensorFlow by creating constant tensor values for our movies and our movie features. To do that, we use tfconstant to create 2 tensors with values for the user movie rating matrix and the movie features. Now we need to scale the movie feature matrix by their ratings given by each user. This will give us a weighted feature matrix for each user. For the first user, we take the rating for each movie and sum by every genre that the movie belongs to. For example, let's take our first user's rating for Star Wars and multiply it by the vector representing the genres. This will result in a weighted feature matrix whose first row consists of 4, 4, 0, 0, and 4. For Dark Knight, the resulting vector is 6, 6, 0, 0, 0. Once you complete this process for all movies for user 1, you'll end up with a weighted feature matrix. Previous operations can be done in TensorFlow in the following way. We first build a list of the weighted feature matrices for each user, then use tf.stack applied to this list, setting the stack axis to be 0. Next, we'll need to find the user feature matrix. We can do this by taking a sum across the genre columns, adding the moving ratings for each genre. The sum of the first genre is colored in blue, while the second is in green, and so on. Once we calculated the sums, we need to normalize by dividing the feature sum by the feature totals for each user. For example, we can take 26, which is the sum in blue, and divide by 67 to get 0.38. We can do this for all other sums as well. Recall that each slice of our matrix represents a single user's weighted feature matrix, so we'll need to do this for each user. To normalize a user's movie features tensor, we first sum each column using tf.reduceSum and setting the axis equal to 1. The resulting tensor would be ranked 2, where each row represents the sum of the feature values for each user. Next, we find the total for each user, again using tf.reduceSum with axis set to 1. The normalization is then just the result of dividing the feature sum by the feature totals for each user. In the end, we stack the resulting tensors together to get the final user's feature tensor. This results in a user feature tensor where each row corresponds to a specific user feature vector. To find the inferred movie rankings for our users, we compute the dot product between each user feature vector and each movie feature vector. In short, we're seeing how similar each user is with respect to each movie as measured across the 5 feature dimensions. For example, for our first user, the dot product between Star Wars gives 0.6. The dot product for The Dark Knight results in 0.5, and so on. We do the same for user 2, user 3, and finally user 4. To achieve this in TensorFlow, we can use the map function. The TensorFlow map function is similar to the map function in NumPy. It repeatedly applies some callable function on a sequence of elements from the first to last. Here, we present that function with a lambda. It's simply the dot product of each user feature vector with each movie feature vector. So, the variable user ratings holds the list of the resulting movie ratings for each user and each movie. We stack them to get a tensor for all the users and their movie ratings. Once we have the user movie ranking matrix, we can improve it and compare it to the original user movie matrix to see which movies to recommend to which user. Because our users have already seen and rated some of our movies, we want to mask the ranking for previously rated movies and focus only on the unrated or unseen movies for each user. So, we only focus on previously unrated movies when providing recommendations. By setting a condition to where the user movie interaction matrix does not have any values, we can return only those rankings for previously unrated movies. This results in this user ranking matrix. Finally, we can use the similarity rankings we've computed here to suggest new movies for each user. For example, for user 1, The Incredibles has a higher similarity score than Blue, and so our new movie recommendation list for the user 1 looks like this. We can also do the same thing for all other users. To achieve this in TensorFlow, we use the tf.where to find the rankings for previously unrated movies and the similarity rankings we've computed here to suggest new movies to the user. Before we move on, let's take a closer look at our third user. She has a rating of 0 for Shrek. Why is that? If we look at the original user movie ratings matrix and compare it with the movie feature matrix, we can see why. Because this user has not rated anything containing comedy or cartoon, and the features of Shrek are solely comedy and cartoon, our recommender system will infer a rating of 0 for that movie. This actually highlights one of the drawbacks of content-based recommender systems. It can be difficult to expand the interests of a user. If a user hasn't rated movies within one of our predefined features, our recommender won't suggest new movies in that genre. In this sense, content-based recommender systems aren't good at expanding the interest of users to new domains. There are some additional challenges with recommender systems. First, cold start. Cold start occurs when not enough interactions exist for users or movies. Second, we could end up in a situation where there's a sparse user and movie space. This occurs when most movies are rated by very few users, or most users rate only a small fraction of movies. Lastly, we could end up having skewed user and a movie space. In this scenario, we either have some users which are very prolific or some movies that are very popular. To summarize, recommender systems are all around us. We've seen how to build a content-based filter using TensorFlow. There are other types of recommender systems, such as collaborative filtering, which I suggest you look at. Each type of recommender system offers its own set of benefits and challenges. Stay tuned for other courses from Pluralsight to help you progress your knowledge in this domain.